Hi all, my name is Vaibhav. I am a research scholar working under the guidance of Professor Ranjini Bandyopadhyay at Raman Research Institute. Topic of my poster is finger, toes, branches and flowers, an experimental study of interfacial patterns formed by the displacement of aging clay suspension in a confined geometry. The picture on the right shows a pattern due to the displacement of one fluid by another fluid, and this pattern emerges due to the Schaff-Mentel instability which occurs when a less viscous fluid displaces a more viscous fluid. These instabilities are sensitive to viscosity contrast between the fluid pair, the interfacial tension and pressure gradient. Depending on the miscibility of the fluid pair used, this instability can be divided into two parts: miscible displacements where the interfacial tension approaches 0, and immiscible displacements where there is a finite value of interfacial tension. So, usually Helios cell is used for studying these instabilities, which is two glass plates separated by a fixed distance, and here this less viscous red fluid is displacing more viscous white fluid, and these instabilities are forming at the interface. For our experiments, we used a synthetic colloidal clay, laponite, and in powder form, laponite particles are stacked together with sodium ions sitting in the intergallery spaces of these tectoids. And when dispersed in water, water invades intergallery spacing and hydrates sodium ions. Due to difference in osmotic pressure, this sodium ions diffuse to the bulk and this tectoid cells. And if the pH of this solvent is below 11, then these particles bear negative charge on their faces and positive charge on their edges. As time progresses, due to this heterogeneous charge distribution and presence of sodium ions, the electrostatic interaction between these particles changes with time and they interact with each other. After sufficiently long time, these fragile microstructures forms and suspension shows soft solid like behavior. We performed rheological measurement to observe the evolution of elastic modulus and viscous modulus as a function of aging time. So, here Tw is the aging time, which is defined as the time elapsed since the preparation of laponite suspension. So, at low aging time, G double prime, which is viscous modulus, is higher than elastic modulus, and suspension behaves as a viscoelastic liquid. Whereas for high aging time, elastic modulus dominates over viscous modulus and suspension behaves as a viscoelastic solid. Here insert shows that at low aging suspension looks like a liquid, whereas at high ages suspension can support its own weight against gravity and behaves as a soft solid. We have also looked at the flow behavior of laponite suspension at different ages and observed that laponite suspension shows shear thinning for all ages and its viscosity decreases with increasing shear rates. So, we have used Helios cell to observe the role of these two parameters on the morphology of interfacial pattern. One is this evolution of elasticity with increasing ages, and another is this shear thinning with increasing shear rates. First, we filled the cell with the laponite suspension and then waited for predetermined amount of time, after which we injected second fluid to displace aged laponite suspension, and second fluid in our case is water or mineral oil. So, these are the patterns that were formed during the displacement of laponite suspension by Newtonian fluid at a fixed injection flow rate and different ages. So, for miscible cases when water displaces laponite suspension, so we see the transition in morphologies from dense viscous pattern to dendritic pattern, and then at sufficiently high ages the pattern displays fracture features. For immiscible cases where mineral oil displaces laponite suspension, we observe a transition from flower patterns which has this dark central region and small toes to this jagged patterns displaying this rough interfaces. We have characterized these patterns in terms of areal ratio, which is defined as the area of the pattern divided by the area of smaller circle enclosing the entire pattern. So, in this picture, the areal ratio is the area of these black pixels divided by area of this red circle. So, for our patterns, we see the areal ratio AP by A decrease with increasing age of laponite suspensions, and it is always larger for immiscible patterns when compared with miscible patterns. Also, we have calculated average branch frequency and average branch width, and we see that average branch frequency is smaller for viscoelastic fractures when compared with the dendritic patterns and dense viscous patterns, and the branch width for immiscible patterns is always more than that for miscible patterns. So here this color bar is based on the logarithmic values of areal ratios, and different colors represent different morphology. We also see that how shear thinning of Laplace suspension will affect the pattern morphology. We displace the Laplace suspension of fixed age, that is 24 hours, by varying the injection flow rate of Newtonian fluid. Here we see for miscible cases, viscoelastic fractures change to dendritic patterns with increasing flow rate, and for immiscible cases, jagged patterns change to flower patterns as the flow rate is increased. Similar analysis is done here also, and areal ratio increases with increasing flow rate for both miscible and immiscible displacements, and areal ratio is always larger for immiscible cases. Finger width for immiscible cases is always larger than that for miscible cases. At last, we used values of areal ratio for constructing a phase diagram with axis representing aging time of Laplace suspension, injection flow rate of Newtonian fluid, and interfacial tension between the fluid pair. Here all patterns segregate themselves based on the logarithmic values of areal ratio. To conclude, we exploit the novel rheology of Laplace suspension to create a range of interfacial patterns, and in addition to parameters such as clay concentration, injection rates, and interfacial tension, our results show that morphologies of the patterns can also be controlled by a parameter called aging time. Thank you.